to section 6.3, performing function operation and composition. We just wrapped up our section 2, which took a look at simplifying radical forms and exponential forms. It was a little bit of a tricky section, a lot of material in there. We're going to change gears a little bit and take a look at what happens when we do addition, subtraction, multiplication, and division of two functions. And then we're going to take a look at what's called composition, and this is where we will substitute a function into the control value of a different function. So a lot of material here today, and we're going to get back into our discussion about domains. So got to make sure we're up on our parent functions if we want to think about graphs, or there's another way we could come up with the domain values if we don't remember our parent functions, and we'll talk about that. All right, so here they are, the operations on functions. Addition and subtraction, those two, you can just think about combining like terms with these. Combining like terms. And the only thing we got to be careful with subtraction is remember that if we're subtracting a function g, my recommendation is put that function in parentheses so that I remember to distribute the negative. So distributing that negative in over there on that example. That's the only thing that will get you in trouble with the subtraction part. Multiplication, two binomial type functions you're foiling, or otherwise you're just using distributive property. Division, pretty straightforward in terms of the operation of division. However, this one is the one we need to be careful of when we're talking about the domains of a division operation. Okay, now, this next statement here, the domain of the new function. So you notice our new function after we combine the f and g, we'll call function h. So the domain of the h function has to consist of the x values that are in the domains of the two original functions, f and g. Now, they have a special case here to watch out for. When you're talking about the domain of the quotient, remember that you cannot divide by 0. So that oftentimes we do this. We have to, not oftentimes, every time we have a division, we should be setting that denominator equal to 0, because in doing so, we're going to find the values of x that make the denominator 0, which means those are actually values of x that your domain cannot be. So you got to be careful with division. All right, in this book, in this textbook, they use some domain notation. ANNR for all non-negative reals, APR for all positive reals, and then all reals. Here's a little symbol we can use for all reals. Now, the ANNR includes the 0, where the APR does not. So, let's see. In terms of inequality notation, like an ANNR would be something that says x's are greater than or equal to 0. APR would be inequality notation, x is greater than 0. And then all reals, we can just say x is equal to all reals. Now, domain notation, you might see it written this way, something like x such that x is all reals. You might see this notation used in the book here. That's what that means. X such that all values of x such that x is equal to all reals, or all values of x such that x is greater than or equal to 0, or all non-negative reals. All right, let's try some examples here. Given two functions f of x and g of x, we want to find what happens when we add and subtract these two. Now, before we get started on any of these, it's always a great idea to look at the functions before you get going on them and think about what their domains are. And both of these are to the 1/3 power, which means they're cubic or cube root functions. And if you remember anything from parent functions, we know that a cube root function, so anything like this, is one of those functions that graph kind of a sideways S curve. And if you look at that curve, you think about values of x that satisfy that graph. Well, it means I can be negatives, I can be 0, I can be positives. And so for both of these cases, for a cube root function, your domain is going to be all reals for both of them. Now, if you didn't know what the function looked like graphically, yes, you could sketch a graph of it. Or you could just ask this question. In the original function, is there a value of x that when I plug it in, produces an imaginary answer for y? So if I plug negative in there for x, I can take the cube root of a negative number, get a negative answer, which is still real. If I plugged a 0 in for x, I can take the cube root of 0, get 0, and then 5 times 0 is 0. That's still real. Put a positive in there, it's still real. So that's the other thing you can be doing, is asking yourself, is there something that x can't be? If I plugged it in for x, it'd give me an imaginary solution for f of x. That would help you determine your domain. So in both of these, all real. So now let's blend them. So we're going to take our f of x, which is 5x to the 1/3. We're going to add that to a negative 11x to the 1/3. And this becomes 5 minus 11. And we have like terms. So we get negative 6x to the 1/3. There's your f of x plus g of x. And notice it's the same kind of a function. It's a cube root function. So in terms of my domain, which we're going to get down to here for part C, we would say that for f plus g of x, my domain would be x is all reals. Or I'm going to use the function in the book, x such that x is all reals. What about g now being subtracted? So we say f of x, 5x to the 1/3 minus negative 11x to the 1/3. Now we're actually adding them together. And we get 16x to the 1/3. And again, a situation where I end up with the same type of function, a cube root function. So the domain can be x's are all reals. Everything works for that value. What about powers of 1/2 now? Adding these together, let's see, we get a 3x to the 1/2 plus a negative 5x to the 1/2 gives me a 3x to the 1/2 minus 5x to the 1/2, which is negative 2x to the 1/2. Now, what were the domains of x to the 1/2? Well, x to the 1/2 are square roots. And again, if you know that a square root function, graphically speaking, looks like that, then you would say x's have to be greater than or equal to 0. If you didn't know that, now you start thinking, okay, can I put a negative in for x? If I put a negative in for x, I can't take the square root of a negative number and get a real solution. So no negatives will work. So the only things that work are the domains have to be x's are greater than or equal to 0s, or in the book's case, a in r. And that would be true of the g of x function too. It must be greater than or equal to 0. All right, we think about that now, and we look at the function that resulted, also a square root function. So we can say that the domain of f plus g would have to be x greater than or equal to 0. Or, again, using their notation, all non-negative reals. What happens when we subtract them? Well, then we get 3x to the 1/2. We're going to subtract a negative 5, which means we add. And we get 8x to the 1/2. So once again, we have a square root function. So domain would be the same. X's must be greater than or equal to 0. Or a in r. I don't need you to do both. Just use either the notation a in r or x is greater than or equal to 0 in this case. we're doing some multiplication and division. So now you're going to have some exponential properties you're going to work with. Let's look at the domains individually first. This is a linear function, so that means x can be all reals. This, now if I were to write it as an exponential change to a radical function, we've got that going on. The sixth root of x to the fifth. And maybe it's easier for you to see it this way. Or just remember, anytime in the fractional exponent when your denominator is even, it's the same thing as an even root, and we know even roots cannot be negative. I cannot take the sixth root of a negative number. And so the domain of this must be x's are greater than or equal to 0 for that one. All right, now we multiply them together. So we have 8x times 2x to the 5/6 power. This gives me 16x. Now, x to the 1 is 6, 6, and I'm going to add 5, 6. So I get 16x to the 11th 6. And then we could do either, let's change it to radical form and get 16 times the 6th root of x to the 11th, and then say we have a group of 6 that goes into an 11 one time, so that means 16 and an x pops out, and then I have x to the 5th left over. Or you could have done, let's work with exponents, 16x to the 11th 6 is the same thing as 6, 6 times x to the 5, 6, which is 16x times x to the 5, 6. And that again takes us back to this radical form. All right, so we have an even root, and that tells me that my domain must be greater than or equal to 0. So here we had a blended linear function, radical function. Linear function said everything could work for x, but the even rooted function there is controlling what my domain is going to be for this multiplication of f and g. So I'd have to say that the domain has to be x's are greater than or equal to 0 for that. Let's see, g of x divided by. So we're going to be careful because it's a division problem here. So we have g of x divided by f of x. Well, I've got 1/4, I know that, and then I have a 5/6 power minus a 6/6 power. Gives me an x to the negative 1/6 over 4, which is a 1/4x to the positive 1/6. And now I want to rationalize that thing, and I want fractional exponents down there. So I want to make it a power of 1, which means if I multiply the top and bottom by x to the 5/6, 5/6 plus 1/6 is 6/6. And I get that. So there's what results there from dividing the two. Before we start looking at the domain of this division problem, we want to go back and consider the very first part, the very first step we did was we wrote the two functions and showed them dividing together. That's where I want to go take a look and see if we got some issues. And we do have some issues with the denominator. In this case, 8 to the x. If I set it equal to 0, x would equal 0. And that's something that we cannot be equal to. So the domain, just in the setup, the denominator part of this says that my domain cannot equal 0. We go back and we look at the result that we get when we divide them, and we notice that the same thing happens. X cannot equal 0 here. If it did, I'd have an undefined value, and that doesn't work. But up in the top, we've got an even-rooted function, which means it can't be negative, so x would have to be greater than or equal to 0. Well, here's a unique situation. We've got a domain in the numerator that says I can be greater than or equal to 0, but the denominator says I can't be equal to 0. And the domains of the division or quotients have to satisfy both of the conditions of the original functions. And so because I cannot equal to 0, I'm going to have to state there that the domain of division between these two must just simply be greater than 0, or this is an APR, all positive reals scenario. So this one ended up controlling the fact that that can't be or equal to 0. It just simply had to be greater than 0 for the domain. All right, so there's a good example of taking a look at our original function domain values, see how they play out, and then look at the result that we get. Let's try this next set here. 7x, and then times an x to the 1/6. Well, that's 7x to the 6/6 plus a 1/6, 7x to the 7/6, which is 7x times x to the 1/6. Or if we wrote it in radical form, we have 7/6 root of x to the 7, which is 7x 6th root of just x. All right. So again, these are the same form. One's radical, one's exponential. Domains, x is all real for that linear function. Domain here, x must be greater than or equal to 0, because again I have a denominator that's even, which means I'm talking about an even root. We ended up with a situation where I had an even root once again, so my domain would say that x's must be greater than or equal to 0 for the multiplication of those two. G of x divided by f of x. So now I've got x to the 1/6 divided by 7x. Again, the only bases are x, so I have 1/7 x to the 1/6 minus 6/6. So that gives me x to the negative 5/6 over 7, or 1 over x to the 5/6. And once again, the denominator that's fractional, I want it to become power of 1. So I'm going to have to multiply x to the 1/6. And we end up with that. The 6th root of x over 7x. I wanted to write it in radical form. All right. And again, taking a look at the originals before I did any simplifying of this quotient. Here we had a domain that said it had to be zeros or greater. Here, again, 7x equal to 0, x equals 0, x cannot equal 0 would be the domain of the denominator, because I can't divide by 0 down. And I see the same thing going on over here, where x cannot equal 0. I see the same thing here, where it says the domain must be greater than or equal to 0. But this is going to change that final solution domain-wise to just simply be x's are greater than or equal to 0, or again, all positive reals. Okay. Where might we see some of these operations going on with functions? Well, we have that here in the world of business. We've got revenues represented by our variable r. We have costs represented by c. And the two equations that correspond to those. So our revenue equation is a function of x is 120x. Our cost equation as a function of x is 2500 plus 75x. Now x is representing the number of printers. All right. Well, let's just stick with the simple part A, and then we'll talk about what actually does this represent, Rx minus C of x. So if we just take our 2, r of x minus c of x, and I have 120 of x minus 7,500 plus 75x, and I'm going to remember that I'm subtracting, so I'm going to stick that c of x function in as parentheses. And that means I'm distributing that negative through. I get 120x minus 7,500 minus 75x, or the 45x minus 7,500. So there's what your r of x minus c of x is going to look like. Now, for part B, what does that mean? Well, in the business world, we have revenues, and that's like money coming in. We have costs. Those are expenses, money going out. And when you find a difference between revenue and costs, you have profit. As long as you have a revenue that's higher, you're going to get profit. If your revenue happens to be lower than your costs, then you're going to get loss. So you're going to have representing profit or loss. It just depends on if the revenue value is bigger or smaller than cost value. So there's an application. All right, talking about the composition now of functions. So now we're not simply adding, subtracting, multiplying, and dividing. We're now putting one function into another one. And here is what's happening in terms of the notation. Here we have g of f of x is what that means. G of f of x. This is a composition function. And we have the f function is going to plug into the x values of our g function. Now this is an important statement, much like it was when we were talking about the operations on functions. When the domain is related to a composition, you have to have the following two conditions met. First condition, the domain of that new function is the set of all x values. So it's all of the x values that satisfy the two conditions. X is in the domain of the f function, the original one that's plugging in, and in the domain of the f of x function, being in the domain of g. So we want x, the domain of f, to be values in the f of x function, and then we want this f of x function, its x values, to be also in the domain of g. And there's a little Venn diagram over here kind of representing that. But let's actually work through some problems and see what this means. Values of x have to satisfy both the original f function and the values have to satisfy the g domain as well. Here we just have a good picture of what composition means using integers. So you can see we've got the notation. F of g of negative 3. And we have our two functions, f of x, 3x minus 4, g of x, x squared minus 1. What's the solution to this? I like to look at composition as like one function eating another one. And if you work from the inside to the out, that's probably a good way of thinking about plugging things in here. So when we say f of g of negative 3, I would love to find out what g of negative 3 is first, because then I can take that value and plug into the x of the f function. So that's what we're going to do. We're going to find out what g of negative 3 is. We take our g function, and wherever there was an x, we're going to put a negative 3 there. And we get 9 minus 1. So g of negative 3 is equal to 8. Now what we can do is we can take that 8 and we can replace in the f of g of negative 3 and get f of 8 now, and now plug that into into our 3x minus 4 equation, where I replace the x this time with an 8. 24 minus 4, and we discover that f of 8 is equal to 20, so f of g of negative 3 is equal to 20. Should have been our answer C here. So there's just showcasing the whole idea of plugging one function into another. All right, now let's try it, though, where we don't plug in an integer value or a whole number, but we actually plug in an entire new function into another function. We're putting an equation into the control variable of another equation. This is the composition piece. We will be looking at their domains. So my recommendation before we get started is find the domains of the individual functions. So 6x to the negative 2 power. We'll go back and look at that one in just a second. 4x plus 5, that's linear. So we know that that's going to be all reals. But this f of x function, let's come over here and take a look at this. 6x to the negative 2. Let's write it as a positive exponent. And we get that. Well, we've got variables in the denominator. And we know that I can't have a 0 in the denominator. So if I were to set x squared equals 0 and square root both sides, I would find that x equals 0. And that's what's telling me what my domain cannot be for this f of x function. So we know that x can be all reals except 0. Okay, with that in mind, now we go and we composite. So we're going to plug f of g. Well, g is equal to 4x plus 5. So wherever there was an x in my f function, I'm going to replace that x with a 4x plus 5. Okay, so we have now 6 over, we're going to make that negative 2 become a positive, 4x plus 5 squared. And yeah, we could go ahead if we wanted to, 4x plus 5 squared, we could write that as 16x squared plus 40x plus 25. We're going to leave it in just this factored form there. So I know that f of g of x would equal this. All right, domain now. Domain. Here we have the g function. All the x's that satisfy g, we said, are all reals. Then we plug that g of x in, and now we want all of the x's that satisfy this f of g of x. Well, in the denominator, we said we're always going to be taking that denominator, we're going to be setting it to 0 to find out the values that x cannot be. So if we did that, we get 4x is equal to negative 5, and x is equal to negative 5/4. So we know that that's the value of x that I cannot be. If I had a negative 5/4 in here, I'd produce a 0 on the bottom. So we're going to say x is equal to all reals, except, you can say it like this, x equals all reals, except x equal negative 5/4, or you could just say x cannot equal negative 5/4. There's the domain of this function. You can be negatives down there. If you square them, you get positive. You can be positive down there. You square them, you get positive. But you cannot be negative 5/4, because that would produce a 0 in the denominator. What if we went the other way? G of f of x. So now we're going to take g of 6 x to the negative 2 power, and that produces a 4 times a 6x to the negative 2 power plus a 5. Okay, let's rewrite this. So this becomes 4 times 6 over x squared. Again, we're just taking that negative exponent, moving it down, plus a 5. And that gives us 24 over x squared plus a 5. If we wanted to write them all with a common denominator, we can take 5 and multiply it by x squared on the top and the bottom. You get 24 plus 5x squared all over x squared. All right, so either of those work. Now, in terms of its domain, we have a situation again where the denominator is going to dictate, and it would say that the domain would set to be all of my real numbers except equal to 0 again for that composite. G of g of x. Well, now we get g of, and we're plugging our g function into itself, 4x plus 5. So now we get equals 4 times 4x plus 5. And then plus 5. All right, 16x plus 20 plus 5 gives me 16x plus 25 is g of g of x. So there's your composite. Now we had a line linear function pointing into a linear function, and here I don't have any denominators to work out, so I can say that my x is equal to all reals for this linear function that I get as a result. All right, there we are, plug-in composites sit together. Let's try a couple more here. F of x equal to 6x to the negative first. Again, thinking about negative exponents. 6x to the negative first is equal to 6 over x. Can't have a value of 0 down there, so the domain x cannot equal 0. Then g of x, 3x plus 5, linear function, it equals all reals. All right, plugging them in. So we have 6 times, and we're plugging in the g. So 3x plus 5, and that is getting raised to the negative 1 power. So this becomes 6 over 3x plus 5. First power, so there's your f of g of x. And then I've got a denominator that I have to check for 0. So 3x equals negative 5, x equals negative 5/3, which means my domain cannot be negative 5/3, because if it was, I would produce a 0 in that denominator. G of f of x. So now we're going to plug in 3 times 6x to the negative first plus 5. All right, this becomes 3 times 6 over x plus 5. that becomes 18 over x plus 5. If I wanted to make common denominators, I'd have 18 plus 5x over x. So there's my g of f of x function. Once again, denominator says I can't be equal to a 0. So my domain would have to be everything except x equals 0. And then how about an f of x? So now we're going to plug a 6 times a 6x to the negative 1, and then raise that to the negative 1 power. 6x to the negative first is going to become that. So now I get a 6, and I get 6 to the negative first, x to the first. This becomes 6 over 6 times x, or just x. So there's what f of x was. Now in terms of its domain, I really have to go back and look right here. I'm going to rewrite this equation 6 times 6x to the negative first to the negative first is the same thing as 1 over 6x to the negative first. And then 6 times 1 over 6, and we can kick that negative 1 power back up. We have that. Well, if I look at that function there, I don't have any variables in the denominator. So it looks like I can be any value of x for this function would satisfy this inequality here. Not inequality, sorry. Would satisfy this composite function. So I can say that x is equal to all reals. Although I can't be equal to a 0 with my original f of x function here. So even though I'm able to simplify it to just x, I still do have to go back and consider this fact that the domain said that 6x to the negative first can't be equal to 0, so I have to go back and reevaluate my position here. So because of that, that's going to have to change my value there. So that's why we go and look at the original functions when we're plugging these things in to see what's happening with my domain values. Even though I've simplified out to become just this, that part of the problem started out where I had 6 times 1 over x. And that 1 over x part is telling me I can't be equal to 0. So be careful of those composites where you have those denominator values. All right, let's try some application in here. I think we were done with our apps there, yeah. All right, so computer sales, you have a coupon for $200 off the price of a personal computer. When you arrive at the store, lucky you, you find that the computers are on sale for 20% off. Let x represent the original price of the computer. Using a function notation to describe your cost f of x use a function notation to describe your cost using only the coupons. So you're fortunate enough where maybe this store allows you to use your coupon of $200 off, and you've got the fact that you've got a sale price going on, which is good for you. Which combination might give you the better deal? Well, let's see what happens here. So use a function notation to describe your cost f of x using only the coupon. So f of x is going to be related to our coupon of $200. So let's see what we have. Our function would be, what's our new price? Well, x is the original price, so we have the original price, and from that original price, we're going to be able to subtract the $200. So, pretty simple. There's your f of x function. Then we've got a situation where we've got a 20% off going on. And so our discount of 20% we will use as our g of x function. So we can say that g of x is equal to, now when you take a percentage off, that percentage off, this discount is coming from the original price. So you're reducing the original price by 20%. That chunk, that 20% of the original price, is what you are subtracting from the original value. So you're doing, with discounts, you're doing this. You take the original amount and you minus 0.2%, 20%, times 0.2%, sorry, just 0.2, which is representative of 20%. So 0.2 times the original. So there's your reducing 20%, subtracting that from the original price. So there are our two functions. One using the $200 off coupon, the other one using the 20% discount. So now we have to decide when we composite them, maybe which of those is going to give me a better deal. So here we're forming the composite of the functions f and g such that we're representing our cost if we use coupon first. So coupon first, which is our f of x function. And then taking our discount, which is our g of x function. So because we're doing our coupon first, what this means is we have a g of f of x. We're doing that coupon first, and then we're going to take that and plug that into the g function. So we're doing a g of f of x here. All right, so if we did that, we have, let's see, our g function is originally x minus 0.2 times x. But we're going to replace the x with our f of x, which is x minus 200. So this becomes x minus 200 minus 0.2 times x minus 200. Okay. Well, what do we get here? Simplifying this, we stick with x minus 200 minus 0.2x plus 20% of 200 is 40. Doing a little combining of like terms, we get g of f of x is equal to 0.8x minus 160. So there's our composite if we did the $200 purchase price off first and then did our discount. Now we're going to go the other way. So now we're going to go f of g of x. All right. So now we take our f function, which is x minus 200, and we're going to replace the x with g of x, which again is x minus 0.2x. And then we're going to take off of that the $200. So we get an x minus 0.2x, which is 0.8x minus 200. And there's your composite if I did the discount first and then took off the money. So our next question then says, would you pay less for the computer if you used the coupon first or if you took the 20% discount first? Well, here we can see the relationship between those two. Here we're going to take $160 off versus $200 off. So I think we're going to end up paying less if we were to do the discount first and then use our $200. There we go.